Okay, I'll just this one. Cancel.
Did you change those grips?
Yeah.
Hi, Neil. I haven't communicated in a while, so yeah, I saw your email. I will print that out.
Okay.
Okay. Didn't hear anything back from chemical physics. We submitted the revisions.
Not yet. I mean, it's only been like. Well, yeah, I guess we're probably here soon.
Hopefully they take something.
Yeah.
Because I think it was minor stuff, right? So
I hope so. I mean,
It's
that's
a-
what it seemed like to me.
it said minor revision.
You know, it didn't
It
specify.
doesn't specify. Okay.
So your sailing was successful?
Yeah, reasonably so. Could have done better in the race, but I wasn't there for the race.
I think you got some sun.
You think so?
Yeah.
Yeah. Yeah.
So where all did it go?
Well, it started in Annapolis, which is pretty close to the top, the northern part of Chesapeake Bay.
Right.
And it's about 110 miles going south to get down to Hampton, Virginia, which is kind of where the ocean is. Then it's another 600 nautical miles to sail from there to Virginia.
Yeah.
That's the big. So they didn't have, the winds were kind of light for the race. And coming back though, so it took them a long time to get the race. It took longer than 2 years ago. But I was waiting on the customs stop when they finally pulled in.
Yeah.
Then on the way back, we had very nice, strong, steady winds. So got in early. Hi, everybody. Hello.
Yeah. I know that. Hi.
I'm sorry, it's longer across campus
No,
than I
no, no.
remember.
You're on time. How are you?
Good.
You look well rested. Like summertime.
It's summer. That's right. It's summer. That's right. I'm on summer schedule.
Good. How are things over on the science side?
Pretty good. I mean, everybody's struggling with funding. Struggling to get funding.
I thought it was just engineering that was having trouble.
Oh, mercy no. I mean, hit rates are like 10%, and then people resubmit. NIH just opened it up so that people can resubmit as many times as they want.
But then everyone resubmits.
Then everyone resubmits, and so the pressure goes up.
Wow.
Funding rates used to be 35%, you know,
Right, which is
decades ago,
reasonable.
which is reasonable, but now they're 10. And there's push to have big joint grants and they have like huge amount of personnel time and a very low probability.
Yeah, yeah.
Hi, Amy.
Audrey.
So it's I mean, used to basically minimum expect everybody going up to tenure to have 2 grants, 2 major grants, and now it's 1 in part.
It's kind of like the humanities almost.
Well, it's not that bad.
That would be bad.
What?
That would be bad.
And costs of doing business have gone up, and even to get a grant, the amount of dollars has gone up.
Right, right. Well, I think everybody's here, and Dr. Lissert wanted to be here, but his son is getting married, so he's up on the way to Boston.
Okay.
Did you set it a higher priority?
No. Just gotta be in two places at once.
Okay. Excuse me, just
Right. But thanks everybody for coming, and this is a great day. Arnaud is going to talk to us about his research, and this is his final defense, and I think you will really enjoy this topic.
Thanks for the introduction, Dr. Levin. So today, I guess the topic and title of my dissertation and presentation would be the use of advanced particle methods in modeling space propulsion and its supersonic expansion. So I'm just going to go through the outline briefly of what you are going to listen to for the next hour. So after a brief introduction regarding the different kinetic particle methods that I'm going to use here, there will be two main parts to this presentation. The first one would be the modeling of ionic liquid electrospray using an MD model. And so the different parts and the evolution the model took will be presented. And so I will start with a constant electric field, move to a one-dimensional model, and then finally the final evolution of the model would be a three-dimensional model coupled to Poisson solver. Then in the second half of the talk, something that's a little bit different, I'm going to introduce and present some results from the study of water expansion plumes and the condensation that took place in those plumes. And finally, coming from those plumes, I'm going to extract some clusters and look in detail at some of the electric properties of one of the clusters, and then I will conclude. So before we get into the meat of things, and in order to not lose some people that might not be familiar with the subject, I'd like to take a few minutes and just introduce the different kinetic particle methods that I'm going to talk about for the next hour. So the first one is molecular dynamics, that's also abbreviated MD. And it was developed in the late 50s, early 60s by two different groups, so the Alder and Wainwright group, and independently by Raman. And eventually, it turned out that both people working on the same idea, on the same algorithms. In MD, the simulation really models the physical movement of the atoms and molecules. And so the interactions between the different particles is coming from a force, and the force is derived from a potential energy that is often computed by the use of quantum mechanics. And the trajectories are determined by solving Newton's equation. And so the applications of MD today is mostly used for chemical physics, material science, and largely for biomolecules. So on the right side here, I just have a picture of a biomolecule interacting with a system. On the other side, the second method that I'm going to use and present in this talk here, in this seminar, is the direct simulation Monte Carlo, also abbreviated DSMC. And it was developed by Professor Graham Bird at the University of Sydney in the 60s. And so that model uses probabilistic methods, so Monte Carlo in this case, to solve the Boltzmann equation for finite Knudsen number. So the Knudsen number that I have, I've put the equation here on this slide, represents the ratio between this lambda here, that's the mean free path, and some characteristic length that we just denote as capital L here. And so when the mean free path is expanded into the different terms, what comes into factor here is the diameter of the molecule that comes into a factor, and this lowercase n here is the number density of the system we're looking at. The reason why we are using this DSMC method here is because the Navier-Stokes equation are not accurate at the Newton number we're interested here. So for rarefied flows, which is the application we're interested here, the Navier-Stokes equation are not accurate, and that's because the transport terms, the calculation is inaccurate. So what we're trying to solve here is the Boltzmann equation. So I have put a form of the Boltzmann equation here, and so the term of interest in this model here is the collisional term, and that's the term that is really the most important one in the model here. So in DSMC, there are different sets of collision models that could be used, and the three main ones are the hard sphere, variable hard sphere, that's known as VHS, and variable soft sphere, VSS model. So at each time step in the model, the collisions are computed. Most physical quantities in DSMC are computed as averages, and so the application of the DSMC are quite broad, but it's ranging anywhere from shuttle reentry to the modeling of some very small system like MEMS. And on this right-hand side here, I have a picture of a reentry, and that's credit to the Japanese aerospace agency. Thank you. So briefly, just to compare head-to-head MD and DSMC, the main differences between the two methods. The application, so MD really could range anywhere from solids to liquid to gas, as long as the density is high enough, whereas DSMC is mostly only applicable to gases. The large difference is very much in the way the particles are simulated, meaning in MD, one physical particle is represented by one computational particle, whereas in the case of DSMC, it could be anywhere from usually 1 million to very, very large numbers. So each computational particle in DSMC is going to simulate a very large number of real physical particles. The interaction, the difference, so in MD, every interaction is based on a force that's computed from a potential interaction, whereas in DSMC, collisions are modeled to model the interactions. The time step is usually much smaller in MD, so in the order of a femtosecond, whereas in DSMC, it varies from a micro to a nanosecond. And in something that's derived from how the time step differs is then the computational size and the length of the simulation. So the simulations are going to be much longer and on much larger domain in the case of DSMC because there are more physical particles being simulated, and also because of the time step that is larger. So now that we have gone through this introduction regarding the different kinetic methods, let's go into the first part here of my work, which focused on an ionic liquid electrospray modeling using an MD model. So briefly, the physics of the device here. So we're looking at what's called a colloid thruster, and the main properties of this colloid thruster and why people are interested in them is because they are relatively low-cost propulsion devices that provide a low thrust but a very high efficiency. So they would not be a device that you would use to make a rocket or a satellite take off, not at all. They would just be used for very small correction of trajectories in space because they're very precise, and sometimes you only need like a micronewton to correct a trajectory for a few seconds. So that would be the use of this colloid thruster. The physics involved in the model here are complex, but basically what happens is that you have a conductive liquid on which you apply an electric force, And when that happens, the liquid separates into a spray of droplets. And later in the process, when the droplets are being emitted, as you can see here, so here you can see the emitter, so usually just a needle that contains the liquid. When you apply the electric field, you form what's called a Taylor cone right here, that's depicted here. And from the cone, on the tip of the cone, usually you have this this cylinder here. That is the jet, and this jet tends to break into a spray of droplets. And so here, at some distance away from the emitter, usually on the order of a micrometer in real devices, you will have an extractor that has a potential difference, and so that's what's creating the electric field. And so those droplets, when they move closer to the extractor, those droplets are charged, and what happens is the so-called Coulomb fission, meaning that the droplets carry a charge that's too large for their size, and they break into small droplets. And that's about it for just the physics of the device. So the key elements that we're interested in here and that are important for the model are the way the potential interactions are modeled, how to initialize the system to make sure when we start the simulation, we start from an equilibrated system. The use of periodic boundary condition in the model is pretty important. But the main challenges really are to reduce the computational effort, because MD, molecular dynamics, are very expensive computations. So in order to do that, we have implemented parallel computing. And when we started this work, it was important to note that at that point, before we did it, as I'm going to show you, no one was able to model a spray of an ionic liquid using MD. So the ionic liquid we're using here, it's called EMIMBF4. Here you have the actual full name that I'm not going to attempt to read right now. But it's used at an ambient temperature, and it has a density that's about 25% larger than that of water at the same ambient temperature of 295 Kelvin. You can see here just the sketch of the molecule. So this is the EMIM plus cation, so it carries a +1 charge on one of the nitrogen atoms. And this is the BF4 minus anion. And you can see that the cation is quite larger than the anion in this particular ionic liquid. In this model, in order to reduce the computational cost, we have used a so-called coarse-grained model for the force field, meaning that this molecule, this EMIM plus cation that contained 25 atoms, was reduced to only 4 particles that are depicted on this on the sketch down here. And so the BF4 minus anion was reduced from 5 to 1 actual particle in the model. So the reduction in the total number of particles went from 25 to 5, increasing the computational efficiency quite a lot. So in this work, we initially started with a so-called simple coarse-grained modeling of the molecule, and it was basically just intuition-based with rigid bonds using Lennard-Jones and Coulomb interactions. We ended up realizing there were some problems. That is, when we tried to just use this simple coarse-grained model to compute the density of the liquid, so we just put it in a box, did a simulation, and kept the temperature constant at 295 Kelvin. What happened is I realized the liquid was not really trying to fill up the entire box, and a large vacuum gap appeared, meaning that the ionic liquid actually wanted to have a density that was about double the one that it was supposed to have in the experiment. So that was quite a big problem. So later on, we switched our focus to something that was a little more developed, and it's the so-called EFCG. That stands for Effective Force Coarse-Grained model. So it was developed by Wang and the Wolf group at the University of Utah, and you can find the reference at the bottom here. In this model, the bonds were flexible, and the potential was tabularized, meaning in our MD program, we had to read in the potential from tables. And when we reproduced the same simulation here to check density, well, it matched density, and you can see there's actually no gap in the system. And the density that we obtained from the simulation was within 2% of the one in the experiment. So that was successful, and that validated the potential model, at least at equilibrium. The first evolution of our electrospray model used just a constant electric field here from the capillary to an emitter that was placed about 1,000 angstroms away. So you can imagine that the emitter was up here. And here you have some characteristic distances. But here I just wanted to show some of the characteristic structures we obtained in the first evolution of the model. So on the right-hand side, on the left-hand side here, you can see a Taylor cone that was formed, and you can see that some ions and droplet here are being emitted from the tip of the cone. So you can clearly see the triangular conical structure here that's formed.
Did you start with just a slab of the ionic liquid and apply the electric field and the cone formed naturally, or did you have some kind of boundary conditions that formed this cone? I
did not have a boundary condition. I did have a mass flow in here. So what happened is that the mass flow was pushing the liquid out. And when the liquid got pushed out, here, right here, anywhere that's on top of this green boundary, there was a constant electric field. Here, 0.5 volt.
I didn't appreciate the brown wasn't a surface, that it was a cylinder with stuff in it.
The brown, yes, that's something I did not mention, so thanks for pointing that out. So this brown here, we're just looking at the side view here, but this is actually a cylinder, so a needle, and the green dots here are the platinum atoms, and they form the capillary. So this is actually a hollow needle that contains all these purple, pink, blue, and green-blue atoms, or beads, basically, here, and those are the ionic liquid. So yes, it's not a slab; it's an actual 3D model.
So in your simulation, this actually is a platinum needle.
Right.
It's a hollow thing that you extrude up and.
Yes. Yes. Well, thanks for pointing that out for the people that are not familiar with it. In the second case here, so here in this case we used a high mass flow, so you can see that it's about 6 times larger than the case on the left-hand side here. What happened with a larger mass flow in the same electric field was that instead of forming a clear Taylor cone with ions being emitted, it formed something that was closer to a jet, a cone jet. That's how it's called. So you have the Taylor cone that turns slowly into a jet, and at some distance further away, this jet tends to disintegrate and separate into some smaller ions and droplets. And finally, on the right-hand side, so here I have a zoom-in view of a case. So it's the same mass flow as the picture on the left-hand side, but here the constant field was 4 times higher. You can see that in that case, there's no more Taylor cone being formed, just because the force and the energy that you apply to the system is so high that it just instantly extracts all these ions right here. And you can see they're just being emitted from a lot of different points. In this case here, it's basically one emission point that's at the tip of the cone, whereas in this case, there's multiple ones. So this ion just got emitted from the left-hand side, then this ion is being emitted from the right-hand side, from the middle, just everywhere. And most of the ions that you can see are very small ions that are like individual, just an EM plus. Generally, whereas in this case, you can see they're quite larger structures, sometimes 7, 8, 9, even above 10. So that's just because we used a very high field here. So that's the impact that the field has.
So what's the charge? I mean, if you have an electric field, it's going to preferentially extract one polarity of ions.
Right. So in this case, with a positive field, it means that there's a negative potential. So what I did, in this case, what it means is that basically your needle's capillary is grounded, and you apply a negative potential up by the extractor. That's what a potential a positive field means. So in that case, it's going to attract the positive groups and charges.
And what happens to the negative ones?
The negative ones, they tend to be emitted in the opposite direction. So that's what you can sort of see right by this lip right here.
Right.
There's some sort of a backflow. So if by any chance, let's say here you have a negative charge that comes out from it, that would be a product of breakup of one of these, what happens is that's going to start moving the opposite direction. once its momentum sort of cancels out, it's going to slowly slow down because you have that force that's trying to slow it down. Eventually, it's going to slow down, go to the 0 point, and start moving backwards. So you have some sort of a backflow. But it usually doesn't happen very much. It happens in some cases. There's some breakup, but usually it happens in this region right here, close to the lip. So that's what you can sort of see on this side right there. Some little bit of backflow. Just briefly, some nomenclature, some of the terms I'm going to use later on when we're going to look at the different currents. So terms I'm going to use are monomer, dimer, trimer. These are the small ions. So a monomer, in the case of the positive one, is an EMIM plus. A dimer is an EMIM BF4 pair plus one EMIM plus. The trimer, as you can imagine, is two neutral pairs with one positive ions. And then, in the same fashion, for a negative case, you replace the EMIM by a BF4 minus. And then anything that is related to as an ion is a monomer, a dimer, or a trimer. So when we look at the ion current, we're looking at the sum of those three terms. In the case of droplets, so a positive droplet, the way I've defined it is any structure that is larger than 9 particles and has a positive charge. So anything neutral would not be a droplet. And in the negative case, it's the same idea, except you would have a negative charge. And so,
by excluding neutral droplets?
I'm not excluding them. It's just that they don't actually exist in the model.
Okay.
So, I mean, I could take them into account. It's just that there's no such thing because
So you always lose any only somewhere.
right. There's never going to be any entity, any group of ions that is neutral and has, let's say, 10 or 12 particles, because it won't see the electric field because it's not a charged entity, so it's not going to travel. It could be a product of breakup, but usually what happens that in that case, when you have a field or an electrical force on it, it's going to break into a smaller group, and it's going to end up being a sum of a positive group, a negative group, and these two are going to travel in the opposite direction. So we just have never encountered large neutral groups.
Okay.
And so finally, when I refer to a torque current, it's the sum of the ion and droplet current. So let's briefly look at some of the currents that are obtained with the constant electric field model. So here we applied a field of 0.5 volt per nanometer. These dashed lines here were measurements that were done by Romero Sands, and we tried to reproduce as closely as possible the experiments, but there were some unknowns in those measurements. So, for example, we didn't really know the distance that Romero used between its emitter and its extractor, and there were other unknowns. So we tried to reproduce as closely as possible. But anyway, so when we use the constant field model, what we saw, and the main conclusion we got out of it is that DMD was overestimating the monomer current. So it's this red curve here. You can see it takes off quite quickly. So here we're looking at the current versus the mass flow. So at low mass flow, the argument was fairly good. But when the mass flow increased, this red curve here took off. And this dashed curve, the experiment that's right down here, is the monomer current in the case of the experiment. So what happened is that since the total current is the sum of all different currents, it also took off in the same fashion as the monomer current. And so the current that we measured or that we computed was quite high, at least 5 to 6 times larger than the experiment. So that was something that needed to be worked on. We believe that this was due to the fact that we overestimated the electric field close to, we overestimated it away from the tip, and that led to an excessive number of droplet breakups. So often when you have droplets that are emitted in the actual experimental device, the field tends to drop when you move further away from the emitter and closer to the extractor. And so those droplets tend to stay, tend to keep a larger size and charge. But in our model, since the field we believe was too high, it tended to break them into smaller entities and often monomers. And that led to a very high monomer current. So those were the conclusions from the constant field, which is why, in a second step, we moved to what we call a one-dimensional electric field model. So what we did here is that we solved Laplace's equation using a PIC model that was separate from the MD model. And so right down here on this black line here, we had put down here the capillary, the platinum capillary, and up on this boundary right down here, we put an extractor, and we computed the electric field. So you can take a look at the electric field in volts per nanometer, and you can see this is a cross section, so it's technically a 3D simulation. But this is the 2D view, and then what we did is that we took a cross section on this x equals 0 angstrom line here, and this is the shape we got for the z component of the electric field, and you can see that the field sort of increases a little bit from the origin here to the red region, and then it starts to drop rather quickly once you move further away in the z direction. So we actually fit this curve, so this data for the electric field to two different. So the first part was a segment, the second one was a polynomial fit. And we implemented this in the model. So we implemented the z component of the electric field versus the distance in the model. And we still kept the electric field in the x and y direction, which are the lateral directions right here. So on the left and the right and out of the screen and back in the wall that you can see here. Those are still kept at 0.
So what is the physics that went into having this variable electric field?
The physics.
I mean, yeah. I mean, did you use a snapshot of your charge distributions from the MD simulation to develop this to solve the?
No, in this first one we just used that Laplace equation, meaning there were no charges involved. We just used the boundary condition.
I suggest you go to the view graph that showed what the yellow pictures actually shows.
Yeah.
It's 2 ahead, 2 or 3.
Oh, this one.
One more. This one.
Yeah. But this one is the 3D model.
I know, but this explains
Right.
the electrical boundary conditions.
Right. So what we did to compute this 1D model is that sort of this yellow domain right here, we put the so this blue cylinder right here is the emitter, so it's the capillary, the needle, and we put this right, we put them in contact in the model, and so here we had the extractor, and we just computed the solution of Laplace's equation in that model, meaning there were no charges involved, just a boundary condition. And from this different boundary condition right here, so what we did is that we grounded here the surface of the emitter, and then we used normal boundary conditions on every other
Is this what I
boundary.
did in E&M back in graduate school or undergraduate, which we used to do conformal mapping and that kind of stuff? All
Yeah,
right.
it's just classical.
So yeah, the only zones that were sort of had direct boundary conditions, so where the potential was fixed at some value with the top of the emitter right here, you can see this red line, and here the extractor that's in the actual 3D model is a ring, so it's a surface between two circles of different radiuses.
Okay, this gives me the I just
Okay.
Right.
sort of jumped into something and I didn't know what physics you were putting in.
Right. That's the idea, but I will get back to that in a lot more detail in a few minutes. But briefly, if we look at the results from the 1D model, we saw improvement compared to the constant electrical field case. So we saw a decrease in the monomer current. It wasn't as high, but it was still over-predicted. So here on the right-hand side, when we look at the monomer current, the red squares were the experiment, the black circles here were the constant field model, and then those two green and blue cases were two different constant electric field that were computed at -13, -15 volts for the voltage of the extractor. So there was an improvement, but still an overestimate, which is why in the final step of this model, we fully coupled the MD software, which here we used DL Party, which is a commercial freeware. We fully coupled that to a Poisson solver that was that was originally developed by my former colleague, Dr. Peng Zheng Wang, and that are sort of modified and really coupled fully to the and actually implemented inside the animal. So I really wrote the subroutines inside the party. But so the driver here of the simulation is DMD software, DL party, and what it does that it solves Newton's equation of motion. So we solve for the velocity and the position at each time step. And so what happens that after the equation of motion are solved, we sort of switch to the Poisson part of the model, and the particles. So in the Poisson model, there's a grid, which there's never grid in MD model. So that was the main part that we had to implement in the model here. Is that we had to create a grid. So what happens is that the particles in the MD model then are being deposited within cells on a computational grid. And then in each cell, the density, the charge density is being computed. Then Poisson equation is being solved. Here you have a discrete form of Poisson equation. I won't go into detail, but basically at every node on the mesh, Poisson equation is being solved using the Poisson solver. And from this, so from computing the potential at each node, we're able to get the electric field by doing a simple finite difference. And finally, once the electric field is computed at each node of the mesh, then by doing an inverse weighting, we're able to compute the electric field at each particles within each cell by doing some interpolation. And so once we have the electric field that is on each particle, again, then we go back to the MD loop, meaning we can compute the electrical force because we know each particle's charge, its field, and so the external force on each particle is just F equals QE, with Q being the charge and E the electric field. And so now we can go back to the MD because we have the external force. And so that's the loop. And so at each time step we do this loop. And that's the idea behind it. So briefly, I'm not going to spend a lot of time on that, but those were the main subroutines involved in the DL party code and the ones that I had to modify. And these were the new subroutines I introduced for my Poisson solver and the way the communication is being done. If someone has a question about this later on, I can spend some time, but I don't think it's very relevant right now for the rest of the presentation. I'm just going to skip in order to keep everyone awake for a little longer. Before I move on to the results, just a couple more considerations here. So some things we realized when we improved our model after some years and months of working on it is that first off, we realized that when we're creating a mass flow inside a capillary, first a capillary, the walls were rigid, meaning the platinum atoms were not moving during simulation. And what we saw happen is that here, this red curve, as you can see when you create the mass flow, initially the simulation starts on 295 Kelvin, but the temperature quickly rises to 400 Kelvin. Now what that means that you use an ionic liquid that has some properties at ambient temperature, 20 degrees Celsius. But after a short time of 100 picosecond, your liquid is already over 100 degrees Celsius, and the properties are very different. The density is different, the way it behaves, the internal energy, everything is very different. So we had to find a solution to get rid of that problem. So what we did is that we introduced a so-called a Langevin thermostat on the platinum atoms of the wall, meaning that the atoms were anchored on the sides by spring, and they could move and dissipate energy. And what that meant is that the temperature remained relatively constant. You can see that the drift in the same time of 100 picosecond with the Langevin thermostat was only 5 degrees Kelvin, which is very acceptable. I mean, there's a little bit of drift, but the difference is very minimal, and the properties of the liquid do not change. Here's the equation for a thermostat. I think it's very relevant for now, so I'm not going to spend a lot of time. If someone has a question later on, let's get back on it. One final consideration is the number of nodes that have to be used in the grid for my Poisson solver. I picked 3 different grids. So the first one was 10 by 10 by 20 cells, so X, Y, and Z directions, and that was the coarse grid. Then I refined all of my cells by a factor of 2, and I called it medium. And the medium was the baseline. case. And then I used a finer mesh that was a refinement of 2 when compared to the medium grid. And what we saw is that when we compared the coarse and the medium grid, the potential, so what we looked at is that we looked at the change in the potential of different nodes. So some of the nodes, obviously, when you introduce twice the number of cells in one direction, some of the nodes will only present in the medium model, but the same nodes that were in the coarse grid were also in the medium grid. So what we did is we looked at the potential and the change on those different nodes, and we computed that. And for the same thing, we looked at the change in the electric field. And so we saw differences between 7% for the potential change and 8% for the electric field change when we move from the coarse to medium model. Then when we compare the medium and the fine model, the difference is only about 2 to 3%. So that means there was some convergence. Now, the fine grid and the medium grid, the computational cost was very high. So I think it was over a factor of 10. It was a factor of 10 to 20. I can't remember the exact number. But it was a lot more expensive to use the fine one. And you can see that the improvement is minimal. So it's about 2 to 3%. So we picked the medium grid, the 20 by 20 by 40, at least in the first model, as the baseline case, and that's what we used. Back to this slide. Now I'm going to have to go in a little more detail. So now in this model, we have to implement boundary conditions. And so, as I've already mentioned, following Dr. Garrison's question, so we looked at 3 different sets of boundary conditions here in this model for the coupled model. And let's just start with the top one that I call the plate boundary condition. Everything on the right-hand side is similar. So differences are going to happen here on this left-hand side first to the emitter. But if you look at the right-hand side, in each case, the extractor is kept at a constant potential of minus 40 volts, so it's a ring right here. It has an opening, a diameter of 300 angstrom and a thickness of 90 angstrom. And the total length of the domain here in the y direction is 500 angstrom. And then the total length in the y direction is 1,000 angstrom. On these lateral boundaries and here in the middle of this, in the hole that is in the middle of the ring, we're only using the Norman boundary condition, meaning keeping the derivative at 0. Now, on the left-hand side, in this first plate boundary condition, the emitter was not put in the domain. It was just put in contact, meaning that the lip of the emitter was the start of the domain. And what we did is that we grounded this entire left-hand side here, as you can see with this thick red line, at a potential of 0 volt. Now, in the needle boundary condition, the only difference here is that instead of grounding this entire plane, we just grounded this circle here that was on the lip of the emitter. So right now, in this needle model, anything that is not on top of the emitter now change from being a grounded potential of 0 volt to, again, a Norman boundary condition when derivatives kept constant 0. In the third model, the tip boundary condition, we actually now moved this emitter that here you can see was depicted in blue. We added to the domain. So we extended the domain by 275 angstrom in this z direction here. And you can see that now we have grounded every single surface of the capillary, meaning the lateral side of the cylinder and the top are kept at a 0 potential. Mind you, this had a big impact on the result, meaning that here, if we're comparing, so here we're just looking at similar pictures, symmetric here, and this green rectangle here is our capillary. And here we don't have any particle in this model. And so in this, on the left-hand side here, we're looking at the needle. So the domain only starts right on this line on top. Whereas in the case of the tip now, this right-hand side here is inside the domain. And what you can see is, what's important here is this very large area of red here. That means that the electric field is very high in this region. So what happened in the needle field, the fact that the emitter was kept outside the domain, we created a very large field right here, right where the particles, so if you can imagine the particles come out here of this capillary, and when they hit this region right here, they see a very high field, and so they disintegrate the entire system and it generates currents that are too high. And so now you can see by moving the capillary inside the domain, what we did is that we displaced this red region to a zone here, a region that's outside of the capillary, but is not really impacted by particles because when these particles are emitted, they're sitting right up there in regions that have much lower fields. So the tip boundary condition was kept as the one that we used for the simulation I'm going to present in the next few minutes.
So go back to the picture. If you had, before you started with these different boundary conditions, did you have some physical insight or gut feeling as to which one was going to be?
No. Here's the main problem. There's no actual experiment measurements of the electric field. No one's ever able to do that.
No, I understand that, but at some point you build a certain amount of intuition or
Right.
thought process.
Right.
Did you anticipate just from your scientific intuition? Do you need to actually have the whole emitter in the field?
I guess initially no. Well, the process where we went from the plate to needle to tip boundary condition was not like it was a process that took a few months, I guess. And initially, we're trying to keep, the goal was to try to keep the domain as small as possible to minimize the cost. So in this first step, we figured, okay, we might have a chance. But then we quickly realized that it wasn't working. So eventually, we transitioned by the needle was the intermediate step, but we had transitioned to this model. And what also happens is that now in this model, at every time step you have, even at the initial time step, you have all the particles that are already inside the system. So the computational time that was involved was higher. So I wouldn't say that we didn't have the intuition. We thought we could work around it to keep the cost lower. It didn't work. So we had to go the expensive way. We had some intuition. We didn't really know exactly the impact. And to really know, we had to do a simulation. We look at these pictures and say, okay, it's a huge impact. And we saw that the way they behaved in space, the model, the particles, just by looking at a snapshot, was very different. So we had a little bit of intuition.
Even looking at the contra-plot for the needle boundary condition, having a big discontinuity there is an issue.
Right.
And how does that affect PhD simulations? I think that's something you kind of not mentioned.
Well, I think I did. What I did say is that the particles, so here's the cylinder, the particles come out here. So what you can see, if the particles here see this field, and let's say right at my pointer there's an ion, what's going to happen is that this ion is going to be emitted with mostly tangential. So here we're only looking at EY, which is a tangential field. So that means that this particle is going to be emitted almost laterally, right here. Whereas what we expect is to see a spray that goes in this direction from from here to the wall, and so in this Z direction. Whereas in this case, the particles, what we saw is that they were traveling in the direction that was privileged, meaning in the Z direction rather than radially. So that was the main difference, the direction which the ions were traveling when they were affected by the field. Does that answer the question? Okay. So finally, now I'm only going to present you the results from the tip boundary condition. So here we're looking at an extraction potential of 40 volts. So the false symbols at the tip model, the open symbols are a constant field of 0.4 volt per nanometer. So if you just do a quick calculation, so you have a potential difference of minus 40 volts and a distance of 1,000 angstrom. If you compute this ratio to get an idea of just the ratio of the electric field, you do 40 volts over 1,000 angstrom, you actually get to this value of 0.4 volt per nanometer. Now, of course, the tip has a variable electric field, the tip boundary condition, whereas the constant field was constant. So, but at least it represents the same sort of amount of energy. And finally, those dashed lines are the experiments from Romero Sands, the same references previously. What we can see in this model is that at low mass flows, so here on the left, so this left plot here shows the monomer, dimer, ion, total current. Whereas here on the right-hand side, the zoomed-in view of the tram and droplet currents, as you can see, they're quite low. So they're in the order of usually 20 to 40 nano amps. Whereas here, the currents we're looking at for total current go up to 1400. So there would have been lines close to the origin, which is why I did the zoomed-in view. But anyways, what you can see is that when you look at the lower mass flow, from 0 to 5, there's usually good argument between the constant model, the tip boundary condition, and the experiment. Now, when the mass flow increases, so at mass flows closer to 10 and 12, you can see that there's still a good fit between the tip, so the full symbols of the tip boundary condition, and the experiment. We're actually even underestimating the currents in this case, whereas if you remember the first model we had a few slides ago, we're quite above the values from the experiment. But here in the case of the constant model, you can see that now it's still overestimating. So there's still quite a divergence that's present at higher mass flows. So it was worth sort of comparing the two models because the constant electric field is quite less expensive computationally compared to the tip boundary condition. And it offers good results at low mass flows, but the argument is not good at high mass flows. So this really validates the tip boundary condition, although it's about 5 to 6 times slower than a constant field model. Some quick consideration to just keep going on these comparisons between different models. Rather than just looking at the currents and the computational time and trying to get a conclusion from that, we try to get a little more of a chemical insight, really trying to figure out how the energy of the system was affected by the boundary condition in the models. So on this plot here, we're comparing the normalized Coulomb energy, so the Coulomb energy per ion of the particles. And what we saw is that the needle and the 1D model were sort of behaving quite similarly, is that the Coulomb energy was increasing. So, I mean, in this case, really, it's increasing because we have a negative, a negative axis, so we're going closer to the origin. They were increasing quite faster than the tip and the constant models. So we sort of separate two groups. The tip boundary condition and the constant electric field behave similarly. And on the other side, the needle and the 1D model behave similarly. And that's because when we derived the 1D model back in the process a couple of years ago, we sort of used boundary conditions that were similar to a needle one. So it comes as no surprise. But really, how the difference can be explained is that they don't behave similarly. And so what we did then is that we looked into detail into the Coulomb energy of the ions that were really emitted. So in this case, we're looking at the entire system. So meaning it takes into account the ions that are still in the capillary. In this case, we just looked at the emitted ions, and we saw in this case quite a difference between the constant electric field and the 1D field. So one value. So the constant field was almost twice as high as, it's actually more than twice larger than the tip boundary condition. So we're comparing minus 0.95 and minus 0.4 electrovolts per ion. And so this was due to the fact that in the constant field model we had larger droplets, over 20 ions. And so large droplets means that you have quite a lot more of the Coulombic interaction, the electrostatic interaction. And so this is what increases this value of the Coulomb energy. To really finish this, just some pictures really to visually show you how this model behave differently. So here in the needle boundary condition, you can see that you have the Taylor cone that turns into a jet, and then you have some droplets here that sort of emit from it. And I did a zoom-in view, so this rectangle here. You can see droplets are rather large, so over 20, sometimes up to 50 ions in there. In the 1D field, you can see that there's quite a lot of spray of ions. So in the zoom-in view, you can see these ions are quite small. They're often just monomers or dimers, or some trimers. And so what's important here is that we're looking at the same mass flow in all models, the same vertical scale, the same number of particles, and the same potential, except in the constant field. So yeah, so the 1D. Then in the case of the needle, so to go back to what I was mentioning a couple of slides ago, right here. So the effect that it had, the fact that the field was very high here right at the lip, now you can really see it, is that this is just a cloud of ions. So rather than moving preferably in this direction from bottom to top, in the z direction, the ions are just everywhere in space. So they're being emitted a lot radially. So you can see just a big cloud of ions. So the needle boundary condition was really not appropriate to this work. And finally, the tip boundary condition here, it behaved a little differently from the constant electric value, although the current argument was good. The constant electric field only applies a field in the z direction, which generates very symmetric results with respect to the x and y directions, so the lateral directions. Whereas in the case of the tip boundary condition, just a small disbalance in the charge initially can lead to quite some asymmetry, because then the field that's being computed could be large on one side, let's say, for example, here on the right-hand side or the left-hand side. So the ions could travel a little preferably on one side rather than the other, because here we're just looking at MD models. So each particle is actually simulated. There's no averaging being done. Just some consideration regarding these droplets. I don't think I'm going to spend a lot of time on that. But one interesting thing we saw in the case of the constant field is that we saw this rather large droplet initially that had the charge of +6, so the normalized charge. And then what happens is that we saw a first coefficient separating into two particles that had a +3 charge, and then the subsequent coefficient reduced it to just a droplet that had a charge of 1. All right. Conclusion for this first part is that, so we really modeled, we started with a constant field model, moved on to a 1D model, and finished with a 3D transient field model that was coupled to a Poisson solver with 3 sets of boundary conditions that were plate, needle, and tip. And really the tip was the one that showed the best results, even though it was quite more expensive than the constant electric field. It was showing better results at higher mass rates. So in this second part, now that we've looked at really an MD model, we're going to look at the DSMC part, where rather than simulate the particles individually, the DSMC is going to really look at larger systems. And so here we're looking at water expansions and how condensation is occurring. Condensation could be a problem. So here we have a picture of the Russian Mir space station, and what happens is that condensation, so this expansion here, water droplets could form and go on solar panels and reduce the performance. So it has an effect on the performance of devices in the flow field. And it could also radiate in plumes and do some contamination. Here we're looking at, so we're going to use the DSMC to look at 2 different sets of experiments. So one is called AEDC, and one was performed by Cato. They're both fairly old experiments, but as I'm going to show you, we got good argument with those 2 cases. And to generate initial sets of particles, I did some MD simulation to investigate the kinetic of the formation of clusters, but I'm not going to show the results here, just due to lack of time. We're using the classical nucleation theory in this model. I think I'm running a little low on time, so I'm not going to go into detail, but if someone has a question, I'll be glad to answer it later in the process. Or it's also in my dissertation in quite detail. So, but basically the 3 main interaction we're looking at the DSMC model are the collisions between molecules, so just monomers, then the collisions between the molecule and the cluster, and then the collisions between clusters. And so those collisions are treated differently in the model, and the nucleation rate here, that's capital J, you can see the equation on top here. Then we compare the classical nucleation theory with a different rate that we just derived from intuition because we realized that the classical nucleation theory was sometimes underestimating the nucleation rate for dimers. So we considered the creation of dimers through a stabilization process that was two-step. Where in the first step, a collision between two monomers created an excited dimer, and then this dimer was stabilized by a secondary collision. The nucleation rate that's involved here is slightly different. But again, this is explained in the dissertation. So first we're looking at the ADC case. And the Newton number is about 0.0001 at the nozzle throat. We look at three different cases. So in the first case, that's called 1A. What we did is that we looked at the values for the heat capacity and the latent heat of vaporization here, that's HV. We used values for bulk water, just values from tables. Then the second case, called 1B, we used values for each cluster, used values that we derived using MD simulation for dimers. And then in the case 1C, we used the cluster size and temperature dependent values of the heat capacity and the latent heat of vaporization. Briefly, so here we're comparing case 1A, so it's using values for bulk water, and at the bottom, the case using the different variable cluster size and temperature. And what we're looking at is the average cluster size that you can see in this case. So here you have the plume, and here's the nozzle, and you can see that the clusters are formed right here in this expansion. So the red zone here shows clusters of size around 300. You can see that if we use bulk value, we predict that clusters being formed are going to be very large, around 300. Now, in the case of the parameters that are specific to small clusters, we only predict value around 100. So it's quite a good, solid change that we saw by sort of improving the modeling of the properties of the cluster. If we look at the temperature, we sort of get the same conclusion. The temperature was higher in the case using just the bulk property. So the fact that we actually properly implemented the values for clusters led to a decrease in the temperature. Not spending a lot of time on this plot, but basically just comparing case 1A, 1B, and 1C. And what you're interested in is really this right-hand side axis, so the right-hand side y-axis, and this red curve, that's the average cluster size. And you can see when you move away from here, your origin, you can see that in the case, so it's just like a sum of what I said earlier, is that the average size of the clusters varies from 275 in the case of the bulk values to about 82 if we used the variable properties for different clusters. So it was a reduction by about a factor of 4 between the two, so it's quite significant. Then we try to compare the Rayleigh scattering intensity from the experiment, so there's red square, and then the computed value, which is this blue line here in the model. And what we saw in this case is that the vapor intensity, so when we did Rayleigh scattering computation, was a few orders of magnitude higher than the cluster. So the cluster really became negligible, and we didn't see large differences, which motivated the next simulation, which is the simulation of an orifice expansion. And we're here trying to reproduce results from an experiment performed by Cato in 1975. And in this simulation, so what the experiment stated is that he used 5 sets of pressure from 100 to 500 torrs and 5 stagnation temperature for 373 and almost 500 kelvins. And so in this case, the reason why we picked it is that the cluster had a much larger impact than in the previous model. So in the previous model, when we look at the Rayleigh scattering intensities, the cluster were quite negligible compared to the vapors. So the reason why we did in this case is that it was quite a larger impact. But basically, by looking at the Moore fraction, so the red curve, we're looking at the number density of the vapor, the green curve, vapor density of the dimers, and you can see that the difference between those two is about an order of magnitude of 1 to 2 when you move further away from the origin. So briefly, so I can move on to the final part here. What we did is that, so here we're looking at the plot of dynamo fraction, which is the important point that we're interested in this model here. So we're looking at the terminal mole fraction, meaning that we placed ourselves, I believe it was 6 normalized diameter away from the orifice, and we measured the dynamo mole fraction, because we mainly had diamonds forming in this case. So the the black squares are the values from Kalo, the experiment, and those 2 green lines were previous computation done by Dr. Zheng Li, the green ones, and then the pink ones were new computations we did, and that were just recently published. But anyways, when we did the comparison between, so the term molecular rate that I introduced early on, that was based on a 2-step process, and the CNT, we saw that the argument was better at high stagnation temperature, and there was a discrepancy at lower stagnation temperature. Now, if we look at the way it behaved when we varied the stagnation pressure for a fixed stagnation temperature, we in this case saw a better argument at higher stagnation temperature. So in the case of 498 kelvins, we saw good argument between our term molecular rate and the Kalo data set. So the argument wasn't as good at low stagnation pressure. So it appears our model performed better at high stagnation temperatures and pressure. I think I'm running quite a long time, so I'm not going to say again what I just presented a couple of minutes ago. But a really important part here is that we did MD simulation, and we used those results to implement a DSMC model. And we validated the use of properties for small cluster in the DSMC rather than using what was done previously, which was using values for bulk orders from the tables. Finally, something a little different at this point is that towards the end of my studies, we became interested in really the formation of different phases of water in expansion. So the different forms water can take on Earth, as you probably know, is liquid water, which the simplest example is just a river. Supercooled water, which is the technical term for really what we refer to as freezing rain. Amorphous ice, which is ice without a cluster, which could be represented as ice cream, because when ice cream is formed, usually it's constantly stirred, so it doesn't get that crystal structure, which is just frozen water, which is more what you have in a sorbet, but what you wouldn't really like in ice cream. So
I hope my ice cream has more than water in it.
well, yeah, but the main part that
it does.
yeah, we're not talking about the dairy part here, but yeah, for the water part, it's large amorphous ice. And finally, crystal ice, and you can see the crystal structures. And all those different phases have different properties, whether it's structural, thermodynamic, or dielectric. So what we did to form clusters, and I'm not going to go into too much detail here, is that we did an MD simulation, a 1D simulation, meaning initially we had this very long and thin box that's depicted by the red dots, and we opened both boundaries here on top and the bottom, and we sort of just let those molecules free flow out of it, and we looked at how the clusters were formed. So initially everything was gaseous and we had those conditions of stagnation, pressure, temperature, and density. And when you see when the plenum was opened, the molecules just free flew out of the initial plenum. You can see the density decreases when you move further away from the initial box. When you look at the statistics of this 1D expansion after 200 picosecond, what you can see is that we look just at the actual velocity, so velocity in this direction of travel versus the normalized position. You can see that the velocity was just, the general trend was the velocity was increasing when it moved further away from the initial position. Then what we did is that we computed the normalized number density, the temperature, and the Mach number of this system, and we basically, so those are the symbols here you can see on this plot, and we computed this versus the position, the normalized position. We did this simple binning process, meaning that we picked a slice in our mole and we average all the particles within that bin. And to validate that, we try to fit those to those solid lines here that represent a simple 1D isentropic expansion theory that you could find in any textbook on fluid mechanics. And the argument was pretty good, meaning that by just doing a simple 1D expansion that neglected a lot of the specs and was not expensive computationally, we're producing capturing most of the physics of the actual isentropic expansion. So what happened is that we saw that by the end of the simulation, we had about 2/3 of the molecules still in gaseous form, and then about the 1/3 left was clusters, so mainly dimers, some trimers, and then there were very few clusters that were a little larger. What was interesting is that we looked at this one cluster referred to as cluster 1. It had a size of 21, and it moved in a perfectly Newtonian manner once it traveled further away from the original position. So here, when we look at the times between 500 and 1,000 picosecond, this cluster was completely isolated, meaning it was just constantly gaining energy because it wasn't experiencing any external force. So it was just infinitely increasing its translational velocity.
Well, you said it has no force, but it's increasing its velocity. That doesn't make sense. If there's no force on it, it should be constant velocity.
The acceleration was constant.
Ah, okay.
Oh, the acceleration.
Okay,
So the velocity was increasing, maybe.
Yeah, you just said it.
All right.
Putting it in a vacuum.
Right.
So
Putting a vacuum in is a constant acceleration, so the velocity just keeps increasing.
So where does that acceleration come from? Is it something you impose, or is it something that what in the system?
Oh, it's the initial interaction. So initially there's a strong attraction repulsion potential between the different water molecules.
Sure.
So when they separate further away,
then they shoot away and they don't interact it. So where does
right? But it's that initial velocity, that initial force that they have initial acceleration.
Sure, but then the acceleration gets removed and they get extruded.
Right.
That when they get removed, that acceleration gets removed. It should go to a constant velocity.
Are you sure the axes are labeled right on that? Let's go back.
So if one molecule just by itself moves into vacuum, it should not have, unless you have electric field, which I don't think you have here.
No.
Y-axis.
The y-axis.
Position, then.
Are you sure that's not? Yeah, you sure that's not position instead of velocity?
Yeah, if it's position, then
No
we are-
problem.
we are-
Because then the derivative is velocity and it's
Oh.
constant.
Yeah.
I think there's a mistake.
The red line is I think the red line is slope.
slope is velocity.
The
Okay.
slope is the velocity, I think.
Yeah, that
Put the one
makes
graph.
That would
sense.
make sense.
Yeah.
But then you should see, if you go to zero, you should see a sort of acceleration, so then there should be a slope, and then you sort of constant.
I think I labeled it wrong here.
Yeah.
Okay.
Sorry about that. So yeah, it's constant acceleration. Thanks for pointing this out.
No. It's not constant.
It's constant velocity.
Constant
It's zero acceleration.
acceleration.
Zero acceleration, constant velocity.
Zero force.
So the temperature of this cluster was actually very low. When you look at the internal temperature, it was in the order of 40 Kelvin, and there's fluctuation with time. There's fluctuation because the size of this cluster fluctuates, meaning there's constant evaporation, condensation of monomers on this cluster, and it sort of constantly changes size. But the average size that we picked was in the order of 21. Right?
21 happens to be, I think, the magic number for one.
Right, so it's always a magic stability number. Now, the fact that we only have one is a little low of a population to claim that it's a more stable structure than another, but it does, as you know very well, happen to be a very stable structure, size 21. Yes. So what we did, so this was the case at 300 Kelvin. So we had that one. We had a couple of those clusters, and the one we looked at was size 21. Then we did a case where we dropped the temperature to 175 Kelvin, and in that case we got a very large cluster of size 324 that was formed, because when we got temperature we got a larger cluster. And we just compared the rate. So we looked at the radial distribution functions, meaning they were sort of depicting the most probable distance between different atoms. So on the left-hand side, we're looking at the oxygen interaction. In the middle, it's oxygen-hydrogen, and on the right-hand side, it's hydrogen-hydrogen. What we saw is that the structure was more defined, and the peaks were narrower at the lower temperatures in the case of the larger cluster. And the peaks match our experimental location for solid ice. Now, when we actually looked at the computed diffusion coefficient of this cluster, and what we saw is that the value was in between the computed value for solid crystal ice and liquid water. So it made us believe that this cluster might have been some sort of a supercooled form in this case too.
What are you looking at the diffusion of it in? This is a cluster.
Yes.
So you're looking at the diffusion of what?
You're evaluating that quantity of there.
Right. Right.
Okay.
So it's a cluster diffusing in.
So is the self-diffusion inside the
Right.
cluster?
It's a self-diffusion coefficient. Yes. Yeah. Self-diffusion. So it's
Within the cluster.
right.
So I would expect that it's sort of hard for me to think about that, but that there would be with a different diffusion for the surface ones than the bulk ones, and so if you have something that small,
Right.
to have a single quantity doesn't sort of make sense. That it
Right. The
stuff
surface and inside, or whatever you want to call it, the atoms and the molecules inside behave quite differently. And we also look at the way the hydrogen bonds were formed, and yeah, they have a completely different behavior. We were just trying to derive one value for this cluster. So this value was derived for the cluster of size 324. The cluster of size 21 was too small to just compute the diffusion coefficient.
Oh, this was a bigger cluster.
Yes, that was the one of size 324. So at that size, we figured it could be acceptable to compute a value. But I mean, again, we're not matching the value of liquid water crystallized, so in between.
But I wouldn't expect that you would.
But you are still a lot colder than liquid water.
Right.
So that's okay.
Right. That's an answer to the question. So this is actually the cluster I was talking about. So the cluster was formed in an expansion plume at 200 kelvins and has a size of 324. And the dotted red lines here represent the hydrogen bonds. And so in this simulation, we always use the TIP4P potential for the one interaction. So it's a rigid model. And the cluster internal temperature was 200 Kelvin when we extracted it from the plume. We did some computation, really to wrap this up, the last part, where we wanted to look at the dielectric properties of water clusters in whichever form they are, and we believe this one might be in a supercooled form. So we wanted first to compute the static dielectric constant, that's usually known as epsilon 0. In the case of liquid water, if you're a little familiar with it, usually the value is, experiments reported around 78, so it's a non-dimensional value. In our simulation, to really look at the dielectric constant, we looked at the fluctuation of the total dipole moment. So just the sum of the charge times the distance of the different groups. So here we're looking at the hydrogens that are charged, and in this TIP4P potential model, the oxygen has no charge, but there's, instead of fourth term, that's called E. So it's a massless term that actually carries the charge. So that's the one we take into account here in the computation of the dipole moment. And so the static dielectric constant in the simulation is computed by looking at the fluctuation here of the dipole moment system. And then you have this constant, this normalization constant in front of it that takes into account the volume of the system and the temperature and the Boltzmann constant. So here we looked at a comparison between the cluster, so this cluster of size 324, that's depicted on top, and liquid. So in the case of liquid, we put a little above 7,000 molecules in a box, ambient temperature, periodic boundary conditions, so really simulate the bulk. And so for the liquid, we got a constant, a dielectric constant value of 53. So you can see that this fluctuation initially for the first 2 to 400 picosecond, and then it stabilizes and fluctuates around some value that can be taken as the average. And the value was found to be 53. And it also happens that people that use TIP4P in the same computation got the existing value of 53. So what it means is that TIP4P has some flows, mainly that it's a rigid model, and so that's why there's some difference with the experimental value. But at least our model, we produced previously published results. Now, in the case of the cluster, we computed the constant in similar fashion, and now we got a value for the constant that was about 8 times lower. So just slightly under 8, in the case of the cluster. So that sort of shows the difference of how a cluster behaves compared to liquid water. So now to really, after looking at just the static dielectric constant, we wanted to look at the entire dielectric relaxation spectrum, and that is obtained from looking at the autocorrelation of the dipole moment. So the autocorrelation function is usually called phi, and here's the expression. So the process is quite complicated, and I'm not going to go into details here. I could if someone had a question later on. But basically here I've plotted the autocorrelation function, again, on top for the cluster, at the bottom for the liquid, on a very short time of 2 picoseconds. And what happened that in the case of the liquid, there's some small oscillations at very short time, under 0.1 picosecond, that are also, we matched those with previously published results. And so by doing a fit of this autocorrelation function after this initial oscillation, this transition time, we were able to compute a relaxation time that's called tau d. And so in the case of liquid, it was 7.7 picosecond, to be compared with the experimental value of 9.6 picosecond, which is good agreement. In the case of the cluster, the value was slightly lower, just above 6 picosecond. So from this autocorrelation function, really what we wanted to get was the complex dielectric constant. So the complex function is the sum of a real term, it's called epsilon prime, and an imaginary part, which is called epsilon double prime. And so to compute this, we had to take the Fourier Laplace transform of the derivative of the autocorrelation function. The expression is a little different between the liquid and the cluster. That's due to the way the boundary conditions and the electrostatic interactions were computed in the two different cases. It was a little different because there were periodic boundary conditions in the case of liquid because we simulate infinite bulk, whereas in the case of a cluster we have a finite size cluster that's isolated in vacuum. And so there were large differences. So here in blue, I'm plotting the real part of the dielectric constant, and the blue is the liquid, and the red is the cluster, and at the bottom I'm plotting the imaginary part. And you can see that there's large differences in those values at the lower frequency, some from a gigahertz to about a terahertz, and then the values tend to merge together at higher frequencies. Now the refractive index, which is something people might be a little more familiar with, just comes from operation on these two values we looked at. So the two, the real and the imaginary part of the dielectric constant, and the conclusions are the same, meaning there's quite a discrepancy between the liquid that's in blue and the cluster in red at lower frequencies. What that means that at those frequencies, so we are in the microwave radiation, what that means is that a microwave is going to propagate about 3.5 times faster for the water cluster than the liquid. But an infrared wave that would be above the terahertz in terms of frequency is going to propagate at fairly similar speed. So that's sort of the impact those numbers have on properties that you might be able to relate to, or just propagation of light and radiations. Now the absorption factor is derived in a fairly similar fashion to the refractive index. But anyways, we're not going into too much details of plots and sort of running out of time. The conclusion we get out of it is that there's more attenuation in a microwave beam when it passes through the liquid than when it passes through the cluster. And in the infrared, the properties are fairly similar. Finally, we looked at the absorption coefficient of the different media, and we saw that the liquid and the cluster were both absorbing and at peaks around 100 reciprocal centimeters, but the liquid tend to absorb quite more, about 3 to 4 times more than the cluster in the same range. There's still some discrepancy with the experiments, so the location of the peaks, and something we're still trying to resolve. We expect that these initial peaks to be located closer to 200 reciprocal centimeters, but right now they're around 80 to 100. Then we expect a secondary peak here around 700 to 800, which is shown in the experiments right here at the bottom. So the experiments from Irvine and Hale. And we don't see it in the MD simulation so far. So we're still working on improving the model and trying to see those because it'd be important to fully reproduce the absorption bands below 1,000 reciprocal centimeters. Finally, we use the me theory, which is explained in the thesis, but the dissertation, I don't have time to go through that. But basically, the important conclusion we want to get out of that is that the me theory tells us that the absorption process, so here we're just looking at the cluster, the absorption process is quite dominant compared to the scattering process in the case of this small cluster. And we also are getting information on the backscattering, so that means we're getting information how detectable those clusters are on like a simple radar that people could use in meteorology, for example, to show you when you look at your phone. If you look at the green area that tells you where the rain is, it's the same kind of idea. So using this backscatter information, we might be able to get precise information on how to detect those particles and how they affect the plume by using a radar. We're still sort of trying to refine those computations, but I mean, here's the results are right now. All right, getting towards the end. Just to really summarize these 1D expansion and dielectric properties. So we did a 1D expansion, got a small cluster of size 21 at 300 Kelvin. We did it the same similar expansion at lower temperature, 175 Kelvin, and we got a large cluster of size 324. We compared those two, and there was some difference in the radial distribution function. But the diffusion coefficient of the large cluster tend to show that it was in the supercooled water form. When we sort of did more computation as far as dielectric properties on this large cluster, it seemed to show that bulk liquid in this cluster were behaving quite differently in the microwave region, but had similar properties in the infrared. One final word on some future work. Maybe someone one day wants to keep working on the selector spray work. I'll only show you result here for one egg liquid, which is EMIM-BF4. I did some other computation on a different egg liquid, which is EMIM-IM. Unfortunately, that egg liquid did not have any coarse grain potential that was published by our researchers, so I'd use an all-atom model. And what that meant is that the computations were almost about a factor of 20 to 50 slower than the ones that I did using the coarse grain model. which were already quite expensive. They were lasting about a week, so that just meant that the computations were not affordable. So in case people would be interested in investigating more detail a new ionic liquid, I think the first step would be to sort of create a coarse grain potential for a new species. Then the second aspect that could be improved with respect to the electrospray work would be maybe to find something that's more robust with respect to the MD code. So right now we were using DL-Poly, which is a software that's mainly developed for biomolecule and equilibrium applications. It turns out that our simulation is very much non-equilibrium. The distance traveled involved are very large, and that sort of caused increasing computational time, and it would not allow us to use a lot of processes. So maybe for future work, if someone's interested, transitioning to a software designed for non-equilibrium could be something valuable. And the final suggestion would be to investigate the use of a non-equilibrium thermostat to really sort of prevent the large increase in temperature in the system. So I suggest the use of a grand canonical, also known as micro VT ensemble, where when one particle leaves the capillary, a new one is regenerated, so to keep the properties inside the capillary very, very similar. And finally, something I just mentioned regarding the water computation was with respect to the location of the absorption bands. We're still working on that, and so we're trying to get a better accuracy between measurements and the values we get to really get these absorption bands at the same location on 200 reciprocal centimeters, that second peak, around 700 to 800 reciprocal centimeters. And on that, the last thing I have to do is to really thank a lot of people. So the support of the AFOSR through those 5 years of research for this grant. Of course, my advisor, Professor Levin, for all the support and the help. Dr. Zhang Li for a lot of support for the years, and all the members of the group that are here today, and the previous ones that were in the group for those 5 years. And finally, my 3 committee members for the help and the suggestions. And the questions they're going to ask me in a few minutes. And on that note, I'm done. Thank you.
Need a break?
I need a sip of water.
Okay, we will take questions from the general audience. If there are any.
I just have some questions on like the structure of the MD calculations.
MD for electrospray?
The first and the second part, I guess.
Okay.
Well, so in the first part, you had like your coarse grain molecule.
Right.
Do you have a feel for what kind of accuracy you lost with that? Did you ever run with like the whole thing? And related, you may have mentioned this, but what kind of computational savings did you get?
So as far as the feel of how comparable it is, we did some computation at equilibrium. So at equilibrium, we got a really good match. So what we computed was the density. So we did an NPT simulation where we sort of let the box size fluctuate. And we looked at the final density, and density was within 2% when we used the effective force model. Now when we used the simple one, the density was about double what we expected. So the simple one, obviously, at equilibrium was not appropriate. There were problems. The effective force was very, it was a very good fit. There were also, we did also, I didn't show it here.
That's compared to experiment or compared to like the whole molecule?
It's compared to MD all atom simulation. So we looked at the radial distribution functions for the effective force, and we got a really good match. The second part of the question was,
what kind of savings does that give you?
So we are going from 25 to 5 atoms. So it's a ratio of 5, and usually we did not measure the savings because we did not run all atom, but it's usually in the order of n squared. So it's about a factor of 25 expected.
Which is what you were finding out, you said at the very end.
Which is when I was basically finding out what I did. So what I did is that for EMI MBF4, I always use coarse grain model. And then at the end, I use this new liquid EMI IM, which is a different molecule. So it's large in size, but it's all atoms. But basically, if I just sort of did a quick comparison by normalizing the number of particles, I got about 25. So it seems to be quite significant.
So kind of related to that, you kind of mentioned switching to a code or software MD that is able to run multiple processes. Are there codes out there that do that, and how does that work? Because I think most of us here can, envision breaking up your domain. It seems to be a lot more difficult.
This one, I mean, all my simulations were actually parallel. Maybe. We can use this one as an example. So mine were parallel. The one thing I was trying to say is that I was limited to only using 8 processes because of the fact that I had a non-equilibrium simulation, meaning that, let's say, in this case, in this box, so this is the box, and in the model you have purely boundary condition. So meaning that really there's 27 neighboring boxes virtually in your model. In this case, since like those molecules are really confined within this box, they're not moving anywhere, and so it's an equilibrium simulation trying to get to the equilibrium point, get a density, get a temperature. You could divide this domain really into, you could use over 1,000 processes and divide into 1,000 different subdomains. What it does it geometrically. So it's going to, let's say if you had 4 nodes, going to cut this in half, and so this top left cube is going to be one domain. Then the next one is going to be one process, and that's how it's doing it. So decomposition is spatial. The problem now, when we have this going on, is that, so as you can imagine, initially the capillary, let's say you divide in 8, and initially it's confined within those grid boundary. What happens when those particles travel right here, they move a very large distance away, up to 2,000–3,000 angstroms. And they're supposed to still be mapped with particles that could still, they're mapped on the same process, particles that are still on this node right here. That's when problems start to arise, because there's just a lot of distance involved. And the way the code's written, it's written to be very efficient at treating a lot of particles, but the fact that there's a lot of distance and the interaction trying to compute in the neighbor list makes it very non-practical.
So it's like, are these newer codes, I'm guessing they're kind of dynamically allocating the area, different regions to
there are some codes that are designed for non-equilibrium simulation, meaning that the decomposition of domain is done a different way, not spatially, but then they're quite less efficient as far as number of particles. So initially,
I mean, you're going to have to, I mean, if you really want to do it, you're going to have to get in and pick some code and fix it for your applications.
right.
I mean, because we've moved, or my collaborators moved to Lance.
Right.
But he spent quite a bit of time, and we do non-equilibrium simulations, adapting it for our set of boundary conditions. I doubt if you will find a code that will just do this.
Oh, no. I guess the problem with DL party is that it's the way the decomposition is done is so deep in the code that it's not something that you can adjust. It's the essence of the code, basically.
Okay.
And we've gotten to the point where we've gone into work. It's just that to really get to the next step, at that point, we know that DL party is almost not appropriate anymore, because you can't just change that. You have to start with something new at that point, because you're asking to do something that it wasn't created, designed for.
So new codes, hybrid sort of approaches where you can decompose in terms of the domain, spatial composition, and let's say the computational work caused by the particles.
Right.
All these carrying out particle interactions, etc. So the new codes, I think they have these graph partitioners that we can tell them, okay, I'm gonna impose 30% of a spatial load and 70% of a particle load. And it's gonna create your processor map so that you can scale it up to not 8,000, for example, 8,000 processors.
Right.
So what kind of codes are you talking about? What names?
I don't really know one's called DMD, but for example, the one I developed is such.
Yeah, but I think that the demands for MD code are a little different. So, all right.
So, I think probably a good idea. What quite often works is a code that is close to what you want to do. If you then write yourself, for example, a Python wrapper around that, it occasionally does some sort of smart decomposition, and then just stop the simulation and continue from there. That can sometimes give you already a lot of. May not be exactly perfect. Like
I think a lot of that was done with DL Poly.
Right.
There's a lot of stopping and
Right,
restarting.
right.
Exactly.
So that at some
Yeah.
point, in order to really move on to like take the next step,
Yeah.
you sort of have to say, well, at some point, that point,
Yes.
if there's something better out there,
And it may take what like Borak is talking about in some kind of real new examination of the computer science. Any other questions from the group? Okay.
There's in electrochemical propulsion, is there any methodization process
that's a
to
good,
get rid of the disadvantage of charged particles?
it's a great question. No, there isn't, because
Would you repeat his question for me?
he asked, so when you have ion thrusters, so let's say like a xenon thruster, where what you do is that you have a xenon bulk gas that you bombard with electrons as a source, and you create a plasma, xenon plus. Then you apply the electric field in a fashion that's sort of similar to that to move your xenon ions, and so that's what creates the thrust and the force and the current. What you have to do in that case is that when those xenon ions sort of quit, so when they reach that extractor and they quit the surface of the spacecraft, there's a very large plasma bulk, xenon plus. What happens is that there's contamination, backflow, and they tend to go stick back and charge the outside of the spacecraft. And now the problem that you have is that you have a satellite that's charged in space, and that, as you can imagine, leads to a lot of problems. So what's being done is that after this plasma exits the spacecraft, there's a bombardment of atoms again to re-neutralize it and bring it from xenon plus to xenon neutral gas to prevent this space charge to happen. So that was the origin of this question. So now to really answer it in this case, the answer is no, because the ionic liquid that you have here, so the reason why you cannot do it is because those structures are very stable in the ionic form. So it's impossible to neutralize a BF4 minus or an EMIN plus.
But people have talked about some schemes, right?
Right. So now that was the answer why you can do it. Now the reason why you don't have to do it is because what you actually do when you operate these, so you're not really that interested about the charging on this one snapshot, on like an instant time, but you're more interested in that into the longer time. And so what's being done is that people alternate the frequency at which they're operating this. So at some frequency, they're altering the polarity, meaning that so if you use a 1 Hz frequency for 1 second, you're going to operate this in a positive mode and emit mostly positive ions and droplets. Then for the next second, you're going to operate in negative mode and emit negative ions and droplets. And so if you look at a longer period of time, you're going to have a general neutrality. But you cannot operate in the same way as the xenon thruster. The thing is that you cannot change the polarity. The only species is always xenon plus. So you always have to run in the same polarity and always create xenon plus and then neutralize them. In this case, you can sort of circumvent that by just changing the polarity, and then the bulk that you will have outside the spacecraft would be generally neutral. So there will be no space charge.
It goes based on 46.
26?
46. Sorry, one page back. So here we see that the percentage of dimers or maybe even trimers increases till 350 Kelvin, and it goes down again. So have you sort of looked at the reason for that?
Oh, that's a good question. Well, at high temperature, so at 530 kelvins, you basically only have vapor. most of those were formed in the plenum, in the chamber. And so it's almost like a sweet spot in between where you're at the low temperatures and you have those very large clusters. You can see 99.7% of larger clusters and no vapor. And then when you're at very high temperatures, you have basically only vapor because the energy involved and the energy you bring from the temperature creates just a lot of fluctuations, and that's larger than the interaction energy that creates the sticking between the different molecules and creates the cluster. So my guess is that it's sort of like a sweet spot, but I guess it might not answer your question as to why it's doing it at those temperatures, or why is there like a peak, or
The problem is you're taking a ratio. I get so bad at my husband's students for taking ratios.
well,
If you would plot the number for each of those, it'd be monotonic trends. but you're changing from a condensed matter to I mean, your physics is right. You've got to
she's absolutely right. If you look at the actual number, the number would be constantly increasing. But if you look at the ratio, if you want to compare it, that's the way the way it shows up in here.
A ratio can get bigger from the numerator getting bigger than the denominator.
Exactly. That's the right answer.
Do you think it's statistically significant, that peak? I mean, I thought maybe, there's a certain, these are averages, these are finite samples. Maybe we don't need to read that much into it.
Well, I mean, here's the trend. At low temperatures, you have large cluster at 175. So you have that large cluster, and then we look at the one of size 324.
Yeah.
And then at high temperature, you only have vapor, basically.
Okay.
So you'd expect that in the middle, you'd have some vapor, some small clusters, and some larger clusters.
Okay.
So it's just that it sort of transitioned this way. If you look at the table, you go from top right to lower left.
Okay.
And that's where the maximum is. So in the middle, you're going to have a maximum in those smaller clusters.
Very good. Okay.
Tom had a question. Oh, unless Nina now. No? Tom.
One per
Okay.
person.
Okay.
So I'm interested in your talk on the different with different mass flow and different electric field. You can
Yes.
have different current, and I would expect therefore different thrust.
Right.
So by showing this variation, I'm going to propose a mass flow and electric field that you can optimize your explicit impulse or thrust.
It's a very good question. I can provide an answer, at least with the material I have right here, as far as, well, not really, because here what I have is, I only have the data for the different boundary condition. But what we did see is that, let me find the backup slide. There's a table somewhere. No, unfortunately, I don't have it.
Well, let's just go back to that table that you had right there.
That one was showing the difference between the thrust and the specific
I know.
impulse.
Yeah.
Yeah, it's something I didn't really go over because
Right.
not that much time. But
So are those differences physically attributable?
yes.
Okay.
Maybe
you can explain.
So what we see is that usually the higher thrust and specific impulse come from having a lot of monomers. And so that's the main reason why we're using EMI and BF4 as the young liquid is because people want to use it in actual devices, and that's why it's been studied in experiments. And the reason why they want to use it, because EMI and BF4 is known to vaporize, well, let me rephrase this. EMI and BF4 is known to operate very much in a ionic regime. So the regime that I define, you can have an ionic regime where you have mostly ions emitted, so monomers, dimers, trimers. You can have a droplet regime where you mainly have large droplets of a few dozens or hundreds of particles that are charged. And then you can have a mixed regime where you have both. And so what's known is that the best the best specific impulses are generated with in the ionic regime. So to go back to your question, you would really have to look at the way the different currents behave with respect to the mass flow. And what you can see is that you create the monomer current is fairly similar, but the droplet currents, which is in black, increases with respect to the mass flow. So you'd expect that when you have more droplets, you would drop your specific impulse. So at higher mass flows, you would have a specific impulse that's slower. So you most likely want to operate at small mass flows.
Anyone else? Okay. If not, then let's just take like a 2-minute break, and then just look at the email.
Thank you.
Stand up and stretch. Thanks, guys. You can take some cooking on your way out. And soft drinks. Oh.
Oh, how was the sailing?
It's good. It's good. Yeah.
That was the progress of the ship every now and then.
Oh, thanks. People checking us out.
How did you do it?
He could have done better, but he did have a podium finish, so I can't complain. Yeah, the coming back was very fast. He has very strong winds. Just
Where were you racing?
Already raced to Bermuda from Annapolis. It's the second time he's done that race.
By himself?
No, he had a crew.
Oh, okay.
I got bumped from the crew, clearance crew, so I just did the return.
Oh, so you flew to Bermuda and then you sailed back. Okay,
When you fly to Bermuda with a one-way ticket, you have to actually go through immigration because they're very nervous about people not leaving.
I'm really surprised you can get a one-way ticket.
You can, yeah.
Okay. And the accident is the one-way ticket cheaper than the two-way?
I assume it is, but I didn't check. But I had to pay $30 because they said.
But I guess if you take a return ticket, you don't charge for the return, they probably get even more nervous.
I suppose.
Oh, that's right. You wouldn't be going through.
You know when, what's his name, Gerald Nietzsche is going to get to campus?
Yeah, January.
January, okay.
Or somewhere between January and April.
Oh, okay.
He opted to wait a semester. Ed O'Brien waited a semester too.